Good morning, Dr. Sumit. Oh, I can't hear you. You're muted.
How are you?
Good. How are you doing?
Good, pretty good.
Thank you so much for doing this webinar for us. Is the other faculties going to be here, Mohammed?
Yeah, he'll join shortly. So I think he has another meeting running.
Should we test out your slides to see if we can able to share your screen and then we can come back?
Yeah, sure. Just give me a second.
How was the weather in Florida?
It's in 70s these days.
Okay, it's 40s here. So he has his own slide and you have your own slide, or we have one integrated slides. How does it?
No,
Because
you will. Yeah, will. I have this copy of the slide, but he will. We have one slide, so he's gonna
share. Okay.
share and then take control over the presentation. I think you can see my slides, right?
Yes, I can. Yes, great. We just want to make sure that it's working. So
Okay.
sometimes it
I have,
takes.
I have this is the backup slide in case he's not able to share, but he'll share.
Okay, sounds good. So we've been doing this webinar series for almost 2.5 years. I think we've been receiving good feedback, and this is the one way to disseminate, what's going on in cybersecurity or smart grid, and the same time for us to network with faculty and see what we can do together in collaboration. Of course, I know you. People know you very well. So I think again, appreciate for being here. We have about 2 more minutes while folks are tuning in. Uh,
Some
is that
AI.
Yeah, go ahead.
I just say some AI thing going on. AI meeting notes. Is that the?
It's just that, yeah, recording of notes.
Oh, I see. I see. Okay. Yeah. I was scared when I see the AI in the meeting. So it's just fine. Yeah.
Is Dr. Mohammad is here?
Should be. He's not here yet. Let me ping
Is
him. Try calling him.
Tanzim, is it who added this AI notes? Julio, I see. Is he our team or who is that? I don't recognize that name.
Yeah,
Hari-
he's running. Okay, just give me 1 minute. So he's coming.
Harish, can you hear me?
Yes, Professor. I removed the AI notes. It won't come up again.
Okay. Well, I just want to know who did that. I think sounds good. Okay. We'll wait for the other speakers and then we can get started.
Yeah, he's connecting. So you have a Thanksgiving break?
Is he here? Harish, can you check if Dr. Mohammed is there on the?
Uh,
I don't see his name
Currently
yet.
don't see him.
I just called him. He's trying to connect.
Should we get started or should we wait? What do you advise, Dr. Sumit?
Yeah, we can get started. I think he
Oh,
will.
yes.
Yeah, he's here. Yeah,
Okay. Uh, Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Sumit Paudyal and Dr. Mohammad Ashiqur Rahman. The title for today's talk is Cyber Physical Resilience of Smart Grid, from Dynamic Attack Design to Adaptive Moving Target Defense. Dr. Sumit is a professor in Department of Electrical and Computer Engineering at FIU. He received MS in Electrical Engineering from University of Saskatchewan, Canada in 2008, and PhD in Electrical Engineering from University of Waterloo, Canada in 2012. He was a faculty member in the Department of Electrical and Computer Engineering at Michigan Technology University from 2012 to 2019. He is a recipient of the National Science Foundation Faculty Early Career Award in 2018 and Etakapa Nu HKN Best Professor of the Year of Teaching at Michigan Tech 2018 and Top Scholar Award FIU 2023. He is currently serving as an associate editor of the IEEE Transaction on Smart Grid. Dr. Paudyal's research activities include distribution grid modeling, optimization, smart grids, PV integration issues, power system control, and protection. And the next speaker, we have two speakers today. We also have Dr. Mohammad Ashiqur Rahman, as an associate professor in the Knight Foundation School of Computing and Information Science at FIU, an associate director for Center for Integrated Security, Privacy, and Trustworthy. He received his PhD in Computing Information System from University of North Carolina at Charlotte in 2015, and BS and MS degrees in Computer Science and Engineering from Bangladesh University of Engineering and Technology. His research interests lie at the intersection of cybersecurity, CPS, AI, with emphasis on attack resilience analysis, security hardening, and resilient system design. His work has been supported by NSF, Department of Energy, and the Department of Defense. Dr. Rahman has authored a book, several book chapters, and over 175 peer-reviewed publications. Thank you so much, Dr. Sumit and Mohammad, for taking the time this morning. It's a great honor for having been here at UND's webinar series. The floor is yours.
Muted, Asik.
You're muted.
Okay, hey, thank you. Thank you, Prakash, for introduction. So let me share my screen. Okay. Yes. You can see it, am I right?
Yes, we can. It's not in full screen, but can you make it?
Now it will be. So my computer got like a very slow. I'm not quite sure why. Especially it's getting old. So the presentation mode will start soon, I hope. Yes. Are you seeing the presenter view or the audience view?
It's good. It's good.
We're good. We're good. Proceed.
Perfect. Perfect. Okay. Okay. So as the title of this talk is like a cyber physical resilience of a smart grid, from dynamic attack design to adaptive moving target defense. And Sumit and me, actually, we are collaborating since 2019. And it worked really well so far. And we have quite a few success with the grants. And of course, our research also has like a many like a sub publications, especially in the area of cyber physical system security. And since Sumit had like a domain knowledge in very much in power grid, that helped me a lot to like see the cyber security in this field. So I'm really like happy to have these presentations together with Sumit. And so when we are during my PhD, actually I started with like working with cyber physical systems security, especially like this power grid. And Duke Energy was had like a project with us, and I was involved there, and that shaped my whole research like concept. And from then, one of the natural question used to be in 2011, 2012 even when I used to talk with the power grid people, they do not want to hear the cybersecurity like a problem for power grid. It looks like it is too much for power griders, how they can do that. But over the time, they figured out like many things are possible. The attacks in like Ukraine, the attacks in like a Stuxnet, that in like a Iranian nuclear power plant. So many things are possible. Now people have a different view. And one of the important part of this like a cyber physical system attacks, if you see like what kind of vulnerabilities we usually see, uh, here confidentiality is not like a big problem. Here the main challenge is whether our critical infrastructure is running properly, optimally. And first thing is like a safety and security. And second part is like a whether it's economically optimal. So two kind of attacks are very problematic here. One is like a denial of service attack, and other one is false data injection attacks. So why these two attacks are more like a problematic? Because our critical infrastructure, which is very much distributed in fashion, where field devices are in geographically in different like locations, they collect data of at those locations and then send the data to the control center to run the system optimally because it is a single system mostly. So if they do not receive the data on time because of denial of service attack, they cannot run it like optimally. So this is very important kind of problem. And another critical problem is you are receiving data, but your data is like a corrupted. By design, cyber physical system, they try to consider the bad data detection. So anything outlier that doesn't match with the overall, this is a single system, it has some kind of like a pattern, um, uh, especially like a Jacobian matrix kind of concept that tells like a relationship between these measurements. So some measurements, if you randomly change them, arbitrary values, you can identify them as outlier and you can remove them. But problem happens when this is very much like a stealthy, when it is an advanced attacker, they can make like a um, still we call it like undetected false data injection attack. In that scenario, it becomes really hard, like how to detect them and how to see the like the attack resilience of the system. And that was basically the research objective of our last 12, 14 years we are doing with this like a cyber physical system, especially in power grid, how we can see the vulnerabilities with respect to stealthy properties, and secondly, how we can detect them and what can be the like the defense mechanisms. So now, so this is like a research overview. If you can try to like a talk in the figure that you have seen here. Um, this shows like some wide area controller. So let me have the cursor laser pointer. Yeah, it will be easier. So okay, so we see that this figure you have like a wide area controller between two areas. It's a simple example, and every area has its own agency. Now they have like a tie lines, and attacker can attacks in different points. It can attack the AGC, automatic generation control. It can attack the AVR PSS, those kind of controls as well. So there are primary control, secondary control, tertiary control. Many things can be attacked. And ultimately, the wide area controller that work between these like areas that can be also attacked, especially tie line measurements and many things can be like um, compromised. Those values can be spoofed or like falsely injected. So the controller may need to work with incorrect data. So this is basically we'll show here. That is the false injection attack is the main focus of this talk today. So now, when we talk about the attacks, one important part was like to know that which kind of attacks we are considering here. So the first kind of attack we usually consider like a man-in-the-middle attack. That basically during the communication you change the measurements. Sometimes you can say that like with this like a modernization of our grid, some kind of encryption cryptography can be applied there. Many of them are basically very old devices, so those group of cryptography is not that like a high like a level. So still they can be attacked. But another problem is always there. The device itself can be compromised. This is like a newer kind of problem where the device is a problem. So communication network might be like a secure, but still you are getting incorrect data. So this is like a two kind of like a threat model we had considered here. So if you see that what we try to do in our analysis, since we need to understand the attack resiliency in automated ways. In the empirical design means you have a test bed, you do your analysis, but you cannot do it for like a larger system. Your test bed is very small range and it's not possible. And so you need something that is automated, non-invasive idea. So to do that, solving the problem where a lot of control optimization is involved, this nonlinear, very much like a complex, like system modeling is not naturally doesn't work like that. So we have different approach, non-linear approach. We try to like use like a linearized version of the essay. So that is a like an important part for us. That means linearization of the power system dynamics. Then we formulate the attack strategy as like a mixed integer linear programming. Of course, we tried like a different approaches, but in this particular case, we try to solve them using like a nonlinear MILP kind of problem solver. Then we apply the attack, and lastly, we try to like verify to see it on a like a opalarity driven like experimentation. So this is the basically the overall goal of these two works that we are going to like present. Maybe Sumit will go over them later on. So the idea is like because of the load change, what kind of um, like a impact we can see. So load change is like a regular process, so you will see some impact. But because of like a forced data injection attack, those attacks are basically not something that is happening in the network. You are giving wrong informations to the like the system. So system is running on like an incorrect understanding of the states, system states. So it will give a like a non-optimal, sometimes that can be malicious for the total system, like those group of control decisions. So this will be like an understanding of attack resilience of the system, how far the damage can be, whether there can be like a cascaded attacks or cascaded impact. So for this injection that I already talked about it. So the idea was like automated generation control or load frequency control. These two kind of things we consider in like a two of our works. These are vital for like a regulating power grid frequency, and they are vulnerable to cyber attacks, as you say, like a two kind of attacks. We consider denial of service attack and forced injection attack. But in this particular two like cases, we was only forced injection. So we try to like figure it out what can be the like the optimal capacity an attacker needs to do an FDIA attacks. So we name it like a OFDIA, so optimal forced injection attacks. This was the idea. So this will actually tell us what a like level of like a capacity an attacker needs to do a like a particular targeted or particular damage oriented attacks. So sometimes we call it impact driven attacks. So this way we will get the attack vectors, and this kind of attack vectors is basically can be continuous that lead to severe consequences like frequency instability. It can be time limited, like that means like it will cause like frequency fluctuations beyond like acceptable range, but that can have like a trigger the possibility of triggering the protection relays. So you are incorrectly triggering a protection relay, not incorrectly. You are taking a decision that's supposed not to be taken, but that generates a like a change in the system that will trigger the relays, and that may like a trip a transmission line or maybe trip a like a generator. So now this like how we model it, like if you see that from a like a context point of view, how we try to like understand the adversary, how we define them. So first, of course, we should have a, like a cyber attack modeling, but then we need a like adversarial capacity. This is very important, what an adversary can do. First thing is whether the particular device or communication link is attackable or not. So we understand like there will be some kind of like accessibility and many other things will be like needs to be like there. There is another property is like whether this is accessible. If attacker do not have like access, remote access or physical access, they won't be able to like attack. And of course, they need to have the right research to like do that job. Once we have this like, kind of like a define this like adversary context, then we have the system information, the cyber physical systems or the control that we are running, and then we solve it using some like for in this case MILP solver that will shows us if there is any attack vectors. If the result is like unsaid, then we may be able to see that there is no like attack vectors. Of course, it cannot do a like a complete verification because of the way the problem cannot tell us like, okay, there is no attack at all. But if it runs for like a very longer time, then we can see that like there may not be any attack. So we think that there is not like a feasible attack vector, so then like something the attacker can get. So as we say, like the attack targets, we consider like frequency of the AGC participating generators and tie line active power deviations that we try to like attack these frequency changes, and the impact will be like a compromised ACE, that is the area control error, will lead to a fluctuation in mechanical input power, rotary speed, and ultimately we will see violation in frequency. Now, Sumit will go over.
Yeah, thanks, Asik, for the nice overview. I'm going to go into the little bit of more in details of this problem formulation that Asik described at the high level. So the objective here is, definitely to if attacker attacks the frequency control, the closed loop frequency control in power grid, uh, we need to learn what is the minimum size of the attack vector, or the minimum compromise it can make on those measurement that can cause the frequency instability on the power grid, or it can disrupt that automatic generation control functionality, right? By triggering the existing relay protection devices on the power network. So you can see two types of setups here. So we first started with a very primitive setup, which is more like kind of a testing the concept. It you can see in the figure A. So we have two area system. So that has generation and it's one control, and so those supplying a load to the transmission line. So the control center measures, the load measurement from the load centers, and then they can dispatch the generator set points to the to the set points to the each of the generators through this closed loop control. So this is, and then when you vary that dispatch, then the frequency of the grid will change. And if you are manipulate that control signal, then frequency can go, beyond the threshold of the relay operations, and then these relays can trip. So the relays installed in the power network which operate based on the under frequency or frequency sorry, as well as what we call the Rokoff based relays as well, rate of change of frequency. So you can manipulate, through these measurements by injecting the false data in these measurements, the actual dynamics of the power grid over the time, and then that can lead to the different frequency dynamics than desired, which can trigger these relays and protection device to trip, unintentional trip of the generator or a large portion of the transmission line, causing the brownout or blackout on the power grid. So and then on this figure B, you can see a little bit detailed version of that. So more realistic scenario where this is the control center works on the measurement, which are typically the measurements of the frequency and tie line flow, coming into the control center. And then if an attacker can compromise those feedback signal, the measurement that comes from the frequency measurement devices and tie line flow devices, when it's communicated, before it's communicated back to the control center, when a false data is injected on that loop. So again, it can cause unintentional dynamics on the power grid that can lead to frequency excursion, and then the change in the Rokoff that can eventually trigger these protection devices. So what we will show here today is how to formulate that, and we are basically formulating that problem from the attacker perspective in the beginning. The reason for that is, even though it's from the attacker perspective, when we develop the protection measures or the mitigation methods, we need to understand what is the smallest attack vector this attacker can inject that can disrupt the power grid without the bad data detection algorithm can detect those false data injection, so that the mitigation strategies could be tweaked so that we can capture those unintentional false data injection attack as well. Though the bad data detection kind of algorithm, which simply relies on threshold kind of approach may not able to catch that. So we need to find out what is that minimum, false data injection vector or the attack vector that can make your system go unstable or unintentional trip of the relays. So we have a bunch of publication that came out as of this as part of this initiative, and then their publication you can refer to if you need detailed models and little bit more insight on the approach. But I will go over Asik. Thanks. I'll go over uh, the in the some details of the mathematical formulation. Like I explained earlier, so this is about finding the optimal false data injection vector. So the problem formulated as an optimization problem. And here the objective is to minimize the attack magnitude and then maximize the impact. That means, so this is from the attacker's point of view to learn how vulnerable the system is and what is the minimum size of the vector that can maximize the adverse impact on the power grid. And here we're looking at the minimization of the time of frequency violation, maximization of the frequency violation. This should be maximized over the frequency threshold so that it can trip the protection devices like under frequency, over frequency, or rook-off relays. We also we should be able to this optimization model basically give you a solution that is going to be stealthy in the sense that whatever the bad data detection algorithm that is already in the place in the system. So this attack vector can go undetected and then make your system still unstable. So the schematic you see on the right hand side is the power grid network. So if you're familiar with how the power system operates, so particularly in the low frequency setup, so you will have control areas, and then the frequencies are measured, the tie lines are measured between those control areas, and then each control area have their own automatic generation controllers that can basically try to bring the frequency and tie-line power flow to the nominal as any disturbance happens in the power grid. And each of those generators or the transmission lines are equipped with those the protection devices like under frequency or frequency relays as well as the rook-off relay. Um, so we have to model those mathematically. So and this basically involves differential algebraic equations, and those equations are highly nonlinear because we have to account for the nonlinear power flow model in the problem formulation. So we adapted this Euler's approximation to discretize and linearize the problem formulation to make it linear, because when it becomes nonlinear, then it is hard to solve, nonlinear programming type of problem, given the non-convex nature of the problem formulation. So we have to look at all the dynamics and control, and also the network topology and information and power flow over the network topology to model that, come up with a comprehensive model of the system that shows the frequency dynamics on the network, and then how that trips the relays during the under frequency or frequency or during the rock-off condition. So these are the set of equations. So if you're not familiar with how the power grid operates, so this is basically the control part, which we call the automatic generation control. Involves a lot of nonlinear and differential and integrations there. And then swing equation is the dynamics of the generator. So and then the DC power flow formulation basically represents the network model. So when we combine them together, so then we basically this represents a system that has a closed loop control based on the frequency, load and frequency measurements, frequency and tie-line power flow measurements, and then it corrects the generation set points to bring the frequency back to the nominal. So that dynamics is basically modeled here and linearized and discretized so that we can formulate a linear problem. which is scalable to tractable to solve from any using any of the self solvers. So now the objective is to maximize the impact by you know creating a scenarios where it can exceed the threshold, frequency threshold for the relays, for the over frequency relays, or it can go below the threshold for the under frequency relays, as well as there are rock-off relays, which basically we have to exceed their rock-off threshold for those relays to operate. So we designed, the problem formulation such that, to include all those variables and then account for those frequency impact on the relays. So the attacker cannot attack the relay directly because the relay operates locally. So based on the local measurements, and hence, so what we're trying to do here is attack the load frequency control loop so that the frequency and rock goes out of bound and then trips the relay. So that's the approach we are taking here, because the relays, most of the relays which basically operate locally, they don't have the wide area information to operate. Okay, so here is the some of the simulation results. So on the left-hand side, you can see basically it shows the dynamics. So it was part of the validation of the model. So we first develop the model in ePhasor which is the simulator that a solver that comes with the polarity. But this one you can model the nonlinear dynamics as is. But in our approach, where we have to find out formulate the problem in an optimization framework, so we converted that to the linear model. So we are basically here validating how close we are in terms of the actual nonlinear model, and you can see the dynamics are pretty representative of the nonlinear. Not using the linear model, we can see similar dynamics very close to the that you can obtain from the nonlinear models. So and then here you can see on the left hand side, sorry, on the right hand side, the figure basically shows. So when there is the attack based on that model, you can see the frequency kind of starts drifting, and then it is continuously increasing. So this is part of like the solution that we obtained from the optimal false data injection attack, and it's very small injection vector on that frequency and tie line power flow measurement. Even that small change, which can be undetected from the bad data detection method, um, is uh, is able to bring that frequency higher than the threshold of the over frequency relays. And so this can trigger the all the relays equipped on those generators, and then eventually trip those generators to make the system go blackout or brown out. So then you can see here there are two type of attack we did. So the previous one was we assume that the attacker has access to that the closed loop continuously. So it's basically trying to inject a small amount of data on that frequency and tile and flow measurement every AGC cycle. So the AGC cycles are basically 2 to 4 second cycles. So every 2 to 4 second of that AGC cycle is injecting small amount of data which is undetected by the bad data detection method. And that is able to bring, and this is in the attacker is doing continuously until it reaches to the it trips the relays, right? While this second one, so we basically assume that the attacker has a limited time, or he cannot access the closed loop control every AGC cycle. So this is basically time bound. After certain time bound, he lost the access to the AGC. But even in that case, we have seen that, so he's able to change the frequency of the grid to the level where it can start tripping some of the relays, right? And some of the overcurrent relays, sorry, over frequency relays and the rock relays. So these two basically demonstrate that you don't need to have, the attacker doesn't need to have the continuous access to the HCC loop. So even if it has a short duration of the, access to the AGC control loop, it can basically cause that damage by creating this injection on the closed loop. Okay, so and here's some more results. So this is basically when you um, let's say that attacker does not have any information of the system, and he is basically naively injecting some arbitrary set of data on that closed loop control, first data injection on that closed loop control, which is not based on the system dynamics, no knowledge of that. Versus when the attacker have some knowledge of the system dynamics, then we have demonstrated that in both cases, this is more like a random arbitrary scenario. The attacker may get lucky to make the system frequency go out of bound if it is doing arbitrary attack, while if the attacker has some sort of the knowledge of the system, then he can systematically design an attack that can for sure make the system go unstable, right? So the first case was more arbitrary. There's no guarantee that that the attacker may reach or may not reach to the frequency may not reach to that threshold, but when it does the systematic attack, so it will definitely go make the frequency go out of bound. So that's the analysis we did on this simulation studies here. Also, when you include or when you do not include the Rokov in the problem formulation, whether you only want to target the over frequency and under frequency relays versus whether you want to target both relays plus the Rokov relays, then the dynamics of the frequency that will evolve over the time with those OFDI attack would be different, because now the target is not only a single relay, but not a single type of relay, but also includes the Rokov type of relays. So that's the result we got. And then the so the bottom line is, why we did design this from the attacker perspective, because now this will give us an idea, okay, what is the minimum size of attack that the system can go undetected, but it still can harm the frequency dynamics on the power grid, and that information now can utilize to design the controllers, or design the mitigation strategies, which is basically our ongoing work. And Back to Asik, so you can now take over the remaining part of the presentation, which talks about some of those aspects as well. And you're muted again.
Hello, you can hear me now, am I right? Okay, I got the control back from Sumit. Okay, so now we are going to like a next level. Basically, this is something our recent work was about, like how we can see the use of like a machine learning in cyber physical system for what will be the new era of like attack structure or attack vectors. So we are seeing that not only cyber, also in CPS, we are using machine learning based tools for intrusion detection system or anomaly detection system. And also like there are controllers like that are recently trying to build using like machine learning based tools, not like a mathematical or physics based model. So this is something like one of our work where we consider like, okay, when we had the previous attacks that we have shown so far, all consider fixed constraints that the attacker needs to bypass to launch a stealthy attack. But that is almost like a very much like a known, very much fixed, most of the time very simple, like some like a threshold values. So the attacker can understand them from like a multiple like interaction, like, okay, this is the place where I can play safely to launch an attack. But the system, there are a lot of dynamics and many other things are involved. So if we use like a machine learning based like an anomaly detection model or ADM, that can basically learn the behavior from history, that means from temporal and spatial data, that means from the previous, is like what has been done and what is currently being done by the others. So it can have like a better understanding of what is like expected and what looks like an anomaly. So this is something that we are trying to see, like, okay, if we have such a like ADM, then how will be our attack vectors? So this was the idea of this work particularly. We try to like see the attack vectors while we have like a machine learning based data detection models. And this paper is basically like under submission, although it is just like I think the minor revision was due and we already submitted that. Hopefully it will be like in publication in like a 1 month or two. Yes. So as you said, that the goal of optimization function is to find a stealthy attack by evading machine learning based anomaly detection model. Ah. Okay, so this figure shows like some scenarios. Okay, let me have my pointer back. Okay, so in the first figure, it shows like the benign scenario, something. So no attack, nothing. It's how these things are happening. And for like a governor and no governor case, then we can see like how this frequency is basically move going down the particular attacks we did here, where we consider the static better detection constraints that previously Sumit just like presented. So now, if we apply like an anomaly-based model, that is actually the figure here, this bottom left figure that shows like a two kind of techniques to do this stuff. The first one is basically DV scan based, one kind of clustering algorithm that is supervised. Second one is like OC SVM. Huh. There's like a one class SVM model. Two kind of like a clustering algorithm has been like used to build this like a machine learning based tool. Although we want to do it using like a DVS scan by nature, by pattern, it will work better and we will show it like later on too. But we just do have a comparison just to show like, okay, if we do not have to run like a supervised model, maybe the OCSVM can be like a way to build this machine like ADM. So as you can see, how we got like a several cluster that shows like this is the benign like a nature of the like a data. So if we go beyond that, that means this is like a outlier. So this is like a bad data that will be considered as like an anomaly. But to model it in as a constraints in our this MILP based or even like a satisfactory model based theories, we need a more linear way to represent that. So we use like a polygon, like a convex hull to represent that like a whole like a cluster. So now the idea is who can do this thing better in which like a particular scenario. If you can see in case of like the right figure, that is for the OCSBM, the cluster boundary is this, and the hull boundary, this convex hull, so the minimum number of uh, like a line that we can consider to get this all the training points, it is much lower. So there's like a lot of like a white space. But in case of like a DVS scan, we see it is very much like a closely could actually see this capture this like a cluster. So that's actually tells that in the next slide we'll see that how the performance will vary with respect to like a which particular cluster we are considering. So as we can see from the figure, this DVS can should perform better because it can better way can see this with the polygon see the cluster. So now let's say go to the a right hand side to this a bottom figure, compare this bottom one with this our top one. So top one was with the static BDD constraints and the bottom one with the dynamic ADM constraint. That is the machine learning based one. And we can see that in this scenario, the attacker needs to launch attack for a longer time to get the similar amount of impact, almost like 75% more. It will need to launch see the similar kind of impact. So this graph, this a tables also shows like a very similar stuff. This is like at a goal is under frequency, and this is over frequency. This relays will be triggered. So we have a rule-based BDD, we have devious scan-based ADM, and we have OCSBM-based ADM. If we compare according to the access to the load measurements, we call it we talked about it earlier, that in the attack model, in the adversary needs to be identified based on its a capacity. So if they have access to or they have resource to attack 5 measurements, how many time slots it will need to get success. So this is like a 2013 kind level of like that many time slots it will need that encompass like a 33 LFC cycle. So the more like measurements it can actually access, the less now time source it will need to get the same attack goal, to achieve the same attack goal. And in case of like a DBA scan, we see that the attacker needs more to 2,800, 2,800 plus. And in case of like a rule-based BDD, they need like only 2,000, little over 2,000, like a time slots to get the same success. And in case of like OCSBM, we see like they need more, but little lower than actually DBS scan ADM. So DBS scan ADM will be like a more attack resilient against like this group of like forward injection attacks. So this shows like the right hand side resilience analysis of the system. It shows like a very another kind of results that shows with respect to the K resiliency. Like when the attack goal is to like you under frequency in case of rule based BDD, when they have access to like that many like times they want to achieve their goal, then the K resiliency the system can tolerate up to 11 arbitrary measurement like changes. So it can tolerate the attack until then, not to have this under frequency tree like a relay to be triggered. So in case of like ML based ADM, then they can have like tolerate more like measurement. In this case, it was 11. They can do like another measurements. It was 12. So this is the way we can say that, especially like you see like many other cases, for example, when they have like a 1,500 time slots to achieve the goal, the target to achieve the goal in 1,500 time slots, K resilience is up to 8, measurements. But in case of like a machine learning based ADM, this is 10 measurements. So this is the way they do like a better. And of course, this is the scalability analysis of the system. And we see like to like solve like a machine learning with ADM, we need like a more time because naturally we have more constraints to like see the cluster using the convex hull to represent that. It creates like a more like a predicates. That's why it takes like a longer time to be executed. So now we'll go to the like the next level. That is basically we are doing in another project, like a recent project that is about moving target defense. And moving target defense is like a one of our like a very much futuristic kind of concept that we have tried to like for like a while. In 2014, for the first time, where we actually talked about it, but over the time, it was like it took little time to like convince the people like okay, this group of defense is very crucial, especially when we are seeing like zero-day attacks and advanced persistent attacker like a threats like when they are nation state like backed, like when for example the attack in like Ukraine was done by Russian that has been identified as like a Russian attackers, and it was expected to be like nation backed. So they have so much money, so have like a creativity, so they can do like a different group of attacks where you may not know them yet. So those group of zero-day attacks, you need to keep your system agile. So that's why this moving target defense is like a very like a important kind of vital solution that can be against those scenarios. So how does it work basically? So it enhances the security of the power grid by dynamically changing the system parameters and configuration. So this has been done for cyber system for a while. From 2010, it was started, and I was one of the like in this group. I was one of the member who tried to like investigate that for like for cyber areas. But then we moved it toward the CPS, where the difference is that from with respect to the other people, some people try to use the cyber like a moving target defense, where they try to like a cyber component change them, change the communication path, change their IP address and many things. But that is basically cyber solution that is applied in many other areas as well. So they just adopt it for cyber physical systems, especially power grid. So, but we try to see it from like a CPS point of view, where you have physics with the cyber. So what we did actually, we try to like do it from the physical, cyber, and control, these 3 point of view. So what is the idea of this moving target defense? Why we want to move? This is naturally, we have seen that any war or any place, we see that sometimes we do not know where this particular person, who is the key person, maybe for that state or for this entities. So they try to move and almost like unknown. So they do not stay in the same place. They keeps like moving so that the enemy cannot actually capture that person and they cannot kill that person might be. So same like idea here. So we will keep moving in a way. Attackers' knowledge would be could become old. So the current infrastructure may not be the current knowledge about the system state will not be there for the attacker. So as that is the things we try to say, any attacks needs to understand my enemy. So that means the power grid here. So without knowing that, the attacker won't be able to do any stealthy attack, because being stealthy means you know the system. So this moving target difference will disrupts the attacker's reconnaissance effort. So ultimately, there are, like as I said, we try to add like a physical and control agility with the known cyber agility to have like a more resilient power grid system. And two kind of like a moving target defense have been seen like here. That is, one is like a proactive, another one is reactive. And we actually try to like do the both job. Mostly our goal is to be like a proactive, but in some cases the attack might be already successful. In that case, we can actually try to move to make the damage like lower the damage. So that's why we also do like a reactive moving. So there's like an important part is that if when you move the system, that means you are changing some parameters. So when you change them, especially the physical parameters, there can be system overhead. And usually if you move it like a very frequently, the system overhead can be like intolerable. So this is very important that there's a trade-off between the defense success and at the same time versus like the system overhead. So this is just an example like how we can do this job. Like for example, in the right-hand side, if you see this hierarchical communication network, we are showing here from a cyber and physical some kind of interaction. So we try to see that if you see that the data is going through RTUs to the next level to the EMS controller. So attacker can attack in the different layers. So it can attack in the RTU as well, try to change the measurements, or it can have a man in the middle attack in different points, maybe in the forwarding nodes. So if they change the data in the RTU level, we may not be able to do a lot, but what we are trying to say, we are trying to change, for example, the data from this RTU, this particular RTU that you can see through my cursor. I change the data ID with some other ID. So we are shuffling them between a set of measurements. So when the attacker will get them to attack, according to the stealthy attack, it may wants to change the measurement 1 and 10, but it will change the measurement maybe 2 and 7. That's why these changes will not be anymore stealthy. They will be look like outlier and traditional machine learning based or even like a validation, a static validation mechanism, they will be able to detect them easily. So that's basically our idea. Now, the point is when you change them in the lower level or different level, in the router level or in the middle, in the forwarding level, change this, shuffling this ID, EMS needs to run on the actual ID, know that this measurement is from that point. Without knowing that the EMS cannot run the control. So how they can remap these shuffled measurements. So there are two approaches we have considered. One is seed-based, other one is prediction-based. Seed-based basically where the measurements are being shuffled, they use a arbitrary number of shuffling, but this arbitrary numbers comes from a seed value. And you know that in a random number, if you have a seed value, they generate the random numbers in the same sequence. So the same seed value will be shared with the EMS, so they know each other. This router is doing some a shuffling, and EMS knows that how this shuffling is happening. So they will know each other. So EMS would be able to work without any problem. But sometimes people may tell that okay, you are sharing the seed. If somebody can reveal the seed, or the seed get compromised, or sometimes because the long run it may be a known to the attacker, then what will happen? In such a scenario, we can have a idea of we are not having any seed based, we can have prediction based, where we try to understand from that data that we are receiving, and of course with the help of some decoy measurements. I would suggest you to read maybe our papers to know the details. So decoy measurements, we can try to like create a case where the EMS will be able to understand from the pattern which measurement it is basically. So the shuffle measurements, it will be able to understand from the understanding of this like intelligence, like, okay, this is originally from that particular location. So this is the way we actually do our job. But in the next level, what we did, we try to like embed them together. Like we have them together. Like we have like for some of the cases, we are applying seed-based. Some of the cases, we are applying like a prediction-based mechanism. The reason was there, both has something good in it. While seed-based mechanism has very good in detection attacks, but they have like other vulnerabilities might be, but prediction-based mechanism do not have those vulnerability of revealing the information, but it has the not like that much success of like detecting the attacks. Although prediction-based sometimes by design, it try to like mitigate the attack impact. Yeah. So anyway, so that has been like done here, like in this like case in the hybrid situation. So here some results you can see. So the deception amount we have has like a RL based optimization like algorithm we created. How much amount of like deception we should apply. This is basically a number of measurements. That means like how many measurements we want to like deceive, we want to like a shuffle, something like that. And we see that like over the time, it like a episode, it runs, it performs like a good, but at some point it looks like it is already trained. So having like a more like maybe training may not give us like a better result. But this is like a deception amount for B is for the prediction preferred scenario. We have seen like a very similar scenario, like what is the amount of like a number of measurements that we can do this like a deception, and also like like this is the case in the second, and the third shows like how this learning is happening. In the third case is basically the hybrid scenario with respective attack detection rate. So this is basically shows like how which measurements we are going to change here. So they learn over the time. So this is basically the lower row figures are more useful to understand their success. As you can see from the figure D, this is for basically detection rate for the seed-based model. And we see most of the time it is drawn in like a different like a direction. So it shows that most of the time the performance is really good. Like in the episode when it was trained well, almost 95% or more time it could actually able to like detect. So the detection was really high. But in case of like a prediction based, we see that the detection rate is not that good. So over the time, somehow it actually basically less than 30%. So in the hybrid model, we see like overall the performance is like close to like a 90% in average. So hybrid model basically work like a detection wise, it worked like a better, but still we prefer the hybrid model because we know that there's like a vulnerability about the seed value can be like a known to the attacker. So with this 90% attack like detection success, still we prefer like this model because it is more resilient against like a such like a attack scenario. So the next shows like another kind of like a case. This is about the physical moving target defense. Here we try to like change the transmission line impact like impedance. So this transmission line impedance can be changed using like a distributed flexible AC transmission system that is very well known as like a FACTS device. So this has been initially like a built to like optimize the overall like efficiency of the system, but we basically leverage those like tools to build this idea. So if you see like from a point of view why it works, so if you have a like an incorrect impedance, the attacker won't be able to compute the attack amount correctly. So they will add some value that might be supposed to be like a plus minus maybe 1 megawatt was supposed to be added to achieve that goal to remain stealthy. They may be like end up adding like a 1.5 megawatt or 2 megawatt because of this like the wrong value to add it as a false data. They will be captured by the static BDD or maybe at least by the traditional machine learning based concept. So it will be very hard to bypass those like ADM or BDD structure security validation models. So this is we have shown here in the case of figure A, optimal defects placement for IEEE 14 bus system. We have several here we have almost 917 defect device, and in case of figure B shows optimal defect placements for MTD to cover all the buses except a bus 8. That is basically a bus 8 does not need any kind of changes, that basically doesn't work because it is almost what do you call it, independently connected to this a network. It has only one connections to the 14 bus system. So we see that a more measurements we have added. For example, three more measurements, these green defect devices we have added, and we place them incrementally. So this is a more a greedy approach where we try to consider the optimality with respect to the criticality of this particular transmission line. So in that situation, we consider the highest critical transmission line. Then once we give a defect device we put at that a transmission line, then we consider the next iteration for the for the remaining lines, which is the most critical now. So this is the way we basically put displacements of the defect devices.
Dr. Mohammed, can we wrap
Yes.
up 1 minute?
Yes. Oh my God, you are very much at the end. Okay, so let me figure it out. So this is something shows really good results, and this is much more efficient than the other parts because it is basically changing the physics itself. So this is something some ongoing research that we are kindly doing. It shows what we have done so far with respect to what a different part of the things that we are doing as a combination, how we see our system. So this is just we have a combined view of our system. As you can see, we have a very last point that we are also doing that we didn't present here. We try to have LSTM based predictive control for denial of service resiliency. So we are trying to build a resilient controller that is by design resilient against denial of service, missing data, or some false data. That is basically we are doing under one of the DOE grants, and that is almost very much a end. So we maybe have the paper ready very soon. So this is the test bed that we built for doing different research, and we didn't show any results from here, but we are having different experiments recently. Hopefully in next 6 months we'll have very good results that is on the hardware in the loop test bed. So this is about another group of work. We try to do a core simulation, and this core simulation becomes a really useful, especially when we have a very complex system. We try to use a physics informed neural network as a digital twin to understand the system and then launch the attack based on that. It makes it much feasible for some cases where even MILP or those group of a linearized model is not also working, especially for EVCS. There are a lot of parties are involved together. It is very hard to do that to in single system. So now in the as we see our research support was basically from DOE. This particular work we also have support from NSF and also some support from National Security Agency. And two recent grants, the ongoing grants we have from Department of Energy, Office of Cybersecurity, Energy Security, and Emergency Response that we are leading basically. So, and we having a few other grants for NNSA, where we also do cybersecurity for power grid. So these are our students who worked and is still working. So some of them already graduated. And so we are very lucky to have these brilliant people. A few of them already joined as a assistant professor. Some of them are in the California ISO. So they are doing really good in their career. So now you will be able to see our publications here. Of course, they are in the IEEE and ACM, their digital, their storage. You will find them, but you will find them also our website. And so thank you. So if you have any questions, are you free to answer?
Thank you, Dr. Sumit and Dr. Mohammad, for making this webinar to us. I think now Let's see if we can, folks can either put their question in the chat. We would appreciate so that we can track those questions.
I have one question, Professor. So I really loved your presentation, and I have a question on this ML model you're using. So could an attacker train a surrogate ML model by observing system responses and then optimize it offline to bypass your ML-based constraints? And how are you planning to mitigate that?
This is basically, you can hear me, am I right? Okay, yeah.
Yeah.
So yeah, this is basically adversarial machine learning, am I right? So attacker can always actually do that job, and this is something like we have several works. Even the last PAGM, we have like one of our work that is for the power gate only, but for other kind of cyber physical system, we have so many works, and it's still the work that we did here that we have presented here, the machine learning base. We solve the problem from a formal point of view. But in the other cases, we solve it from reinforcement learning and many other like a known like attack point of view. But the idea for in such a case, actually how this adversarial machine learning and all this stuff so work, we do not have like enough like a data. That's why we have some places where our system is very much like overly taking decisions according to some points. If the attacker can knows those points of where it is basically giving more weights, it can play with that. Like, okay, it can change like some other points where it cannot figure it out like whether it's an attack or not. It will see it as a benign because it is basically relying on the information that was given to it, not the whole structure, whole place. So the idea is how you can create your knowledge space like a large, how you can defend them. This is the only way you can do it. So doing that is basically means you can use like a GAN to create a more like attacks, similar attacks, so that you can reduce your like a unknown space. And also you can have like a transformer model or something that is by design, try to see it from a point of view, it can expand its like a knowledge when it get trained. So this is something is has been done so far, but we are also trying to see it from like a multimodal point of view. That may not be exactly it depends on the context, but we did it for other cyber physical systems where we consider the side channel kind of data. That is not attackers control. So attacker change the measurements. Yeah.
Okay, we have a number of questions. If we can keep the response very brief, then I
Okay,
think.
okay, sure,
Okay,
sure,
thank
sure.
you. Hello, Professor. For the very nice presentation. I am from the Khalifa University. I have one doubt because I am working on the smart meter security on the data side. So I have lot of 5-year data, or I have implemented machine learning algorithms as well as deep learning algorithm also. And one more things, I have created the 5 different attack scenario, 5% attack to 20%, 5, 10, 15, and 20%. So I have one query. When I increase the attack scenario, then performance of the machine learning algorithm is decrease. And it's perform around 5% scenario, 10% scenario perform good. And when increase the attack scenario, the classification of the attack, the performance will reduce.
What is your question?
Okay, I think I got the point. So I think what you have seen, you've got, I think this group of questions, more specific ones, we can do it like offline. You can send me an email. I'll be very happy to help. Seriously. It looks like I'm contributing. But the point is here, the reason is very clear. If you see, when you have 5% attack scenario, it performs better. What I have answered in the last question, you have some unknown space. When you have 10% attacks, when you have 15%, 20%, you are going toward those unknown space. You are giving more attack scenario might be that this model was not trained yet. If it is the something like that you are asking, if I understood the question correctly. If I not, maybe we can discuss like offline, okay?
I want to go back to the next question I have, which is related to your presentation. On your numeric analysis slide, the N/A indicates the attack did not succeed at all. Am I reading that correctly? If that's true, why in just that one case?
Which slide is it?
You had a slide called titled numerical analysis.
The table. You said the table with. Can you go back?
Okay, so I think I can answer that question like offline, okay? Because I cannot recall that explicitly that one. Really good. Thanks for this question. Very few people can have this question. So you're talking about this table, am I right?
Yeah, I think this one. You
Not
can see the.
applicable, am I right? So OF not applicable,
Yes.
am I right? So I need to see that basically exactly like what is the scenario here. So I cannot recall the case where we couldn't actually hold these things for over frequency.
Okay.
Okay. So maybe there's like a scenario there. So we couldn't actually find like a scenario where we can have this. Okay.
Okay, so can I
So
ask
just
a
like,
question?
yeah,
Yes,
yeah,
Dr. Junlu, please
Okay,
proceed.
so can I ask a question? So
sure.
I don't know whether I followed correctly where with your the presentation. It seems to me that this presentation go along the discussion that suppose all the cyber protection all has been breached, and then under that assumption, then how of from the control perspective, to trying to mitigate of the possible attack. So doing the research along this line, I really want to ask, and how much you think you will be able to tolerate. It seems like, assuming that all the cyber protection all got gone, and what will be the tolerance that, your design will be able to somehow still mitigate, any, arbitrarily large, of the cyber attack.
Okay, so I think this is the question that we always try to answer. This is something was from our like a beginning. We define a term known as attack resiliency. Why we define the term? Because like how much my attack I can tolerate. So attacker may want to achieve some goal, but having like a 3 or 4 measurements, if they have access, they won't be able to reach that goal. But if they have more capacity, they will be able to reach that goal. So it is more about how you see your attacker's capability. If you think that attacker has a very like a large capacity, then they will be able to launch that attack. Then you cannot do anything. Okay, forget about that. But you know that that level of capacity they won't have because there are some access restriction. There are some different level of you can like a protections layers are there. So they may not be able to achieve that level. But nation-backed attackers, why we always say that this is like a real problem, because they spend a lot of time, they spend a lot of money to be successful. In that situation, really, we have very less things to do. But as we said, if you see that here, like we talk about the K resilience, am I right? So you can increase the attackers like expense by adding like a more like a hard. For example, the DBS scan ADM we had, if we had like a better model, more like a few like a another transformer based GAN based LSTM and transformer based that we are kind of doing, that can increase this K resiliency maybe to 16. 10 it may become 16. So attackers, we can think that that level of attackers may not be possible to have that many access. This is the one way. And the another way that we talked actually at the end, that was basically designing like a resilient controller. So I know that some measurements will be missing. I know that some measurements may have positive injection. Can I still tolerate that from the knowledge from the other who was not compromised yet? So more towards having like a wide area control or like a distributed control where some failures can be mitigated by the other like a nodes which are not compromised yet.
I see, I see. So that which means that this approach, assuming that the system is not fully naked. Okay, so however, just trying to deal with some false through, of the attack, assuming that the major part of the cyber attack will be somehow gets withheld, by the other portion of the cyber protection. Is it fair to say this?
We can tell that. This is like a
Okay.
lot of
Anyway,
arguments are basically there. So we can tell like a many ways we can see it. It is basically context driven, problem driven. And truly different system has different level of like a security. Uh, it is truly like the way, even, the topology, based on the topology of a power grid, their critical will be like a different, just for your topology, like a design.
Mhm.
This is very like so more interconnected ones are less hard to do a stealthy attack, because change in one place understood by the others, or you may be able to impute the unknown or the compromised data. Like, okay, this is bad data. Okay, how is the imputed data? Maybe you will have more redundancy. But redundancy solve a lot of problems naturally, and that we do from the beginning. Power Grid always do like a redundancy. They take like a lot of measurements that they may not need. But so this redundancy defense in depth, this is the way we should design our like any cyber solution, that must come with some understanding, like there can be a security hole.
Okay.
Okay.
We are
Okay.
12
Thank you.
minutes, we're 12 minutes past the presentation. I appreciate for being here. I think thank you, Dr. Sumit and Mohammad, for doing this webinar for us. And you will receive a nice plaque from UND as part of your contribution. And people can reach out to you for further questions. I know that we had a couple more questions we didn't answer. I'm just trying to look at the time, but I think it's very interesting presentation. I appreciate for being here this morning with us.
Yeah.
Thank you, Prakash.
Thank you. Feel free to email us. Like I believe you guys can go to the website and get Sumit's and my like email address. Okay. Thank you guys. Okay. Bye.